Oh, I was muted. I'm afraid. Okay, so rewind. So let me start from the front. So what will be the 2 next hours about? So once again, it will be first hour will be about 3 talks. One by myself, an overview talk, Julia for HPC. Then one remote talk by Mose Giordano from London, who will speak a little bit about how Julia can adapt to normal uh, computing processors, and then Ludovic Rees from ETH Zurich, who will talk about GPU computing. And then in the second hour, we will do a short HPC mini tutorial. And those of you who have gotten login credentials, unfortunately, not everyone. I tried to explain this in the email yesterday. But those of you who have the credentials can do it on Nocto 2. Everyone else can follow along, and you will still have a great experience. Right. So once again, what is HPC? I want to talk a little bit about the term, what it is about. It is related to supercomputers, of course. But once again, HPC is that, am I doing HPC if I run my code on a supercomputer? Is that about it? And the point is, well, first of all, I would say you can also do HPC outside of a supercomputer. That's my personal opinion. But even if we take, the Wikipedia stance that we have to be on a cluster or a supercomputer, efficiency certainly matters, right? Like if you naively go to a supercomputer and I don't know, run a single core computation, right? You're not utilizing the hardware. So I wouldn't call that HPC, high performance computing in the literal sense. Then there's also the traditional viewpoint, the traditionalist view from the Fortran and C++ guys and so on. Well, you're not using MPI, you're not doing HPC, right? Like if you don't use the entire cluster and 10K plus cores, right? I don't care what you're doing, right? That's some stands by some people. What about GPUs, right? Even if you think about that, one A100 has more compute these days than even multiple CPU nodes, depending on which cluster you're on. So, well, I don't use MPI, but maybe I just run on one A100. Is this HPC now, right? So what I'm trying to get at, and one more thing, what about sort of high throughput computations where I just do trivial parallelization? I just run the same code, replicas of it, right? So trivial HPC, if you want, right? So there are different, ways to utilize supercomputers. And in my personal opinion, right, I want to have an inclusive picture in mind of HPC. All of this counts to me, right? If you care about performance, you're interested in supercomputers, be it GPUs or IPUs or CPUs, I don't care, right? You can contact me, and I want to want you to have a great Julia experience for whatever you're doing. Where I come from has already been mentioned a second ago. So traditionally, by training, I'm a condensed matter physicist. So I did my PhD in Cologne in condensed matter quantum field theory, actually. So I also had some bosons and fermions. So I know a little bit about also a Higgs transition. I didn't call it a Higgs transition, but okay, whatever. I'm sort of a foreigner in the sense that, I'm not doing high energy physics. But still, we share a lot of the methodology, like quantum Monte Carlo simulations and so on. And eventually, throughout my PhD, right, I ended up eventually running, stuff for 50 million CPU core hours, producing lots of data, and sort of got pulled into HPC, if you will. And that's also what I want to show with that plot. I started as a pure domain scientist. In fact, during my master's, I didn't use computers at all, or like pretty much, apart from emails and whatever. So I started as a domain scientist, and at some point I just figured out I need to, if I want to solve that problem, I have to go to supercomputers. And Julia was the tool that enabled this for me, like quite literally. I tried C++ and everything, and I programmed in the past in C++. But Julia for me really was the tool that, first of all, brought my code from my laptop to the supercomputer, but also brought me personally from physics to HPC. So now I work in the National High Performance Computing Alliance in Germany. And this is my first point that I want to make about Julia. So basically making a case for why Julia could be a good choice for HPC. And the first is kind of a social point, that it can make HPC more inclusive. At least that's what I hope and what I think it can do. So basically make people transition that maybe just start very innocently on a laptop doing, caring a little bit about this benchmark, and then asking questions about how can I make it faster, right? And before they know it, they talk to me on a cluster and are parallelizing their code. At least that's the vision, right? So that there's no barrier, like hard barrier. You know, that's a version of the two-language problem, which you might have heard about, right? But not just in the development kind of interpretation that we typically hear, but here in the sense of gravitating or basically moving to different architectures or in also a different domain. Right, and we are in Erlangen here, so I thought I'd bring up this example. So NHR at FAU, it's one of our fellow national HPC centers here in Erlangen. It's actually not far away from here, 5 minutes, I think. And together with them, or basically they develop a tool here, which is called Liquid. By the way, a great name. It stands for like I knew what I'm doing, which characterizes a lot of feelings on HPC clusters, I think. So great name, great tool. What does it do? It basically allows you to measure the performance of a piece of code on a hardware level. So it's not measuring on the software side, timing things, but literally in the hardware, in the CPU cores, there are performance counters that measure what the CPU has done. You know, how many flops has it performed? How many, I don't know, data has it transferred from memory? And you can read out, like if you know what I'm doing, right? I can read out these performance counters and figure out what the CPU has done. It's very tricky, very difficult if you try it manually. And that's why Liquid exists. It's basically the abstraction layer that makes this usable for you. And I wrote, in collaboration with those guys, I wrote the Julia package for it. And obviously, and Liquid is like typically a command line tool, right? You just run it from the command line and so on. And I wrote it in a way that you can use it interactively. And here, as a sort of speaking to the vision that I just showed, without you knowing you are doing HPC-like things. So here I combine a very high-level thing, Pluto, right? This reactive notebook interface in a browser, with some very low-level stuff. The HPC people at NHR at FAU developed Liquid, and I combined the two things. So what am I doing here? And this is the video, I hope. Yeah. So I have a computation, and what I use Liquid for is to count the number of flops that have been performed by the computation. And what you can see is I changed the Julia code, right? I added one more flop to it, one more floating point operation, and this counted flops is an interpolated markdown variable. So basically, I spit out markdown, but it's a variable under the hood. And through this reactivity, I can change all of this. It reevaluates all the time, looks at the CPU counters underneath. So this is, one example where I want to show that Julia has potential before even talking about other technical aspects that you are probably expecting in this talk, about some inclusive potential here, right? I can typically, the first time I used Liquid, I had to go to a talk which was called Node Level Performance Engineering. I listened to, 500 slides of low-level stuff, and then they introduced Liquid as a command line tool, right? And this I can do in a course with people who have never ever, wondered about CPUs before and so on. So this is, so again, the social aspect, which is close to my heart. That's why I bring it up here. All right, but apart from this, Julia can be fast. I'll keep this short because, the case is made. There are multiple examples. We have heard this at least once or twice this morning already. Many cases. So left is my quantum Monte Carlo code that I developed during my PhD compared to Fortran C++. On the right is some computational fluid dynamics code, and we are competitive. And, we are at a point you might wonder, oh, the blue line, it's so much better, so much lower than the Fluxo, which is a Fortran code, the orange line. Well, at the end, right, if you have a language that can be fast, it just matters how much, effort do you spend? How much do you know your algorithm? How much do you know your hardware? And how much time do you dedicate to optimizing it? So once again, this is not saying that Julia is faster, intrinsically faster than Fortran. It's just, that they spent more effort here. Julia can be parallel. So we'll talk a little bit about multi-threading in the tutorial later, but here I show MPI parallel. So that's the same CFD code that I showed on the last slide. And this is a strong scaling plot. So basically just saying I, increase the number of parallel resources that I have, in that case, MPI ranks. And I go actually up to 60,000 ranks. So this is, I don't remember how many it was per node, but eventually this is, like a good chunk of the cluster, if not even the entire cluster this was run on. So this is distributed computing at scale. And you just see that, you get a great speed up. And GPUs, again, we'll hear more from that in Ludovic's talk later. But just to pitch this here, they put a stencil computation on a cluster of, it wasn't A100, it was a different kind of GPU, but they reached very good parallel efficiency, almost 100%, like 96 or 95, whatever. And in that case, better than C, but once again, that's not the key point, the key takeaway here. Julia can also be generic. So Mose, I think he won't talk about this today in his talk, which I'll bring this up here. He benchmarked on Fugaku, which at the time I think was the fastest supercomputer in the world. And it's an interesting one because it's ARM-based. And Mose just put like BLAS on there, like in this case, single-threaded, I think, and just benchmarked the XPy operation, which we'll be more concerned with in the tutorial in a second. And he compared it to, different BLAS implementations. Blue is the Julia one. The rest is, the other colors. You see Julia is competitive. And that was for single precision. He also did double precision with a similar outcome. And on the right, you see half precision. And it's pretty lonely there because none of those BLAS libraries support float 16 on Fugaku, but Julia does, right? So for him, it was just trivial, change the type, and it just ran. And the other vendor libraries, even the vendor library, right, Fujitsu Plus, just didn't support it, right? So Julia has something to offer here, like fast adoption, and again, more on not on this exact matter, but something similar in Mose's talk. Julia code is portable, right? Even before you start diving into MPI and utilizing the parallel resources, is so good just to go to a cluster, type in one command, and have your code running. Right? If you've ever, maintained other software, it's a hassle. And obviously, this is also a lot thanks to Mose, as we've learned this morning, with binary builder and so on. So this includes CUDA and MKL and all of that stuff, at least if you want. In some cases, it's not that easy, though, because you might need to run system software, like a system MPI or a system CUDA. Sometimes you have to, because literally there's no other way to use the internet interconnects between nodes with the CUDA JLLs or MPI JLL. But nonetheless, this is a huge, and this reminds me of something I did in a workshop 2 weeks ago, where I actually showed, Julia for HPC and all the fancy things. And then I thought I should show plotting. It sounds trivial, right? But you can't plot in C++, at least not, natively. So we forget about these things. We forget about that, we take it as granted. We say, okay, we can do this and then go to the pain points. But, we should appreciate that stuff. Obviously, there are also new challenges. So I like this plot from Michael Schlotke-Larkemper and the Trixie team, who scaled, Trixie, and there's also some ordinary diffie-Q involved there for obvious reasons. And he scaled it to 16K ranks. So that's, again, an MPI parallel simulation. And what he found is that the Julia depot gets under a lot of pressure. So what you see here is that, once you start at, let's say, 2,000, 4,000 ranks around that, you see a stark increase in the total JIT overhead, which is, using a package, like typing using Trixie or using ordinary diffie-Q, and then calling your function for the first time, excluding the runtime, right? This is what the blue line is, all of that together. And the other lines are just the separate components that I just mentioned. So if you take the purple line, for example, no offense, Chris, right? But just using ordinary diffie-Q on 60K MPI ranks took like, I don't know, 10 minutes, right? And no, actually, this was precompiled. This was precompiled. There's no precompilation. This is literally, you have everything precompiled. I have to say this was 1.8, though. It was before 1.9. But nonetheless, right, this is a problem. That's all I want to say, right? You run into new challenges, 15 minutes just waiting before your code actually runs, right? This is a problem. And, the long story short, location matters. The way they solved this is they copied the depot into the RAM drive / temp on every node, and then everything was fast. But obviously, there's some overhead, some management going on. Memory footprint, can be big of Julia. If you run it in parallel, you pay it multiple times. Increases since 1.8. I don't have the slide here, the plot here, but unfortunately, it's increasing. Maybe it will go down at some point again. Multi-threading plus GC. The GC, while parallel, stop the world is an issue that we basically hamper the multi-threading performance by it. So there are many more challenges that I could mention here. Workflow, getting used to interactivity at scale, right? We are used to There's REPL workflow and so on. It doesn't translate one-to-one onto clusters where you have a scheduler and all that stuff. So tooling, many things I could mention, but there are these challenges. Who is using Julia for HPC? So I put a bunch of people here, or actually projects or initiatives. The Climber project, which is very well known at Caltech. So Simon Byrne, for example, is a name that you might have heard there. Basically, I solve climate simulations, seismics, exascale simulations at MIT. Valentin is also involved there. Valentin Shuravi, Trixie at Aachen and HLS and a bunch of other places. Computational fluid dynamics, Michael Schlotke-Larkemper. They running MPI parallel at large scale, GPU for Geo, right? Ludovic's talk will be maybe about this in a bit. So they are from Switzerland and doing, computational earth science there. So a lot of people are using it. It's fun to be part of. If you want to be part of, there's an HPC community. You can find us on the Slack. We run a monthly HPC call that you can join, where you could talk to, we have an agenda, you can bring up points. You can also just join and don't say a word for 1 hour. That's also fine and perfectly acceptable if you just want to tune in. And you find us at conferences, a bunch of conferences I list here. One is next week, SE23 in Denver. So if you happen to be there, there will be a Birds of Feather session and, some nice stuff. We also wrote a little position paper, which we put on the archive. I linked it here. Summarizing, to leave some space for questions, Julia can be a great option for HPC. Performance can be great. Portability, hyperactivity, there's much to gain from using Julia instead of other languages on clusters. New opportunities, interactive HPC. We'll see some of that in a second in the tutorial. But obviously, there are these new challenges, some of which I mentioned. We have to get used to it. For some, we have to find solutions. Some of them are hard. Some of them are just, it's just a matter of time to fix it or a matter of manpower to fix it. And obviously, you pay the early adoption cost, right? Julia HPC is obviously niche. Lack of support tooling, you pay the price sometimes, right? There's not, tons of documentation that you can check and so on. So this is something to consider when using Julia for HPC. However, the Julia HPC for community, it might be small, but it's very vibrant. It's very fun to be a part of it. And niche also has an advantage, right? The ways to, or the communication paths to people are short, right? Like you can very quickly build a good network around the globe. So yeah, feel free to join us. And more from me in the tutorial. And for now, some questions maybe. And then afterwards, Moses.